Thank you. Okay, so I'm doing context switching in the Linux kernel. That's my presentation today. So my name is Sharad. I'm a second year. I'm from Fairfax, Virginia, which is somewhere around DC. Let's go. Yeah, let's fucking go. So I'm on co-op right now. I work for a small company called High Peak Cyber. I do as an engineering intern. My main work focuses on exploitation and reverse engineering of like various hypervisors for bootloaders and kernels. Recently, I've been working on a lot of Android stuff, and specifically Android trusted execution environments at EL3 for ARM. I do a lot of low level. I enjoy ARM64 assembly a lot, like way too much. And of course, Arch Linux is for bitches. Okay, anyway, so the objective of this presentation. So the objective of this presentation is to go over the ARM64 context switch code path. I didn't do x86 because I did ARM for my job. And I learned the code path at my job, and I didn't want to relearn the x86 code path. So if you're into x86, well, tough luck. Yeah. So intro to scheduling. So before we actually talk about what a context switch is, we first need to discuss the concept of scheduling. So scheduling is the process by which an OS decides which process to run and for how long. So generally, on a computer, you have your big CPU, and each CPU has a bunch of threads on it, which can run concurrent processes. The OS needs to decide which process is using which thread and for how long it's using that particular thread. So typically in scheduling, we have the concept of a time slice. The time slice is how long a process can run on a particular thread. Once the time slice is over, it's kicked off the thread, typically. So one big question is, how does a computer tell when a context switch needs to happen? So generally, a computer does not have a sense of time. And that's a problem that a particular device actually fixes. Before we discuss that device, we first need to discuss IRQs. So IRQs are the way devices communicate with the CPU. So typically, if a device needs attention, it'll essentially trigger an IRQ line, and that'll tell the CPU to run the ISR, or the interrupt service routine. And that essentially is a software handler for the device. Typically, the ISR is located in the driver or somewhere similar around there. So in x86, the entry point for the ISR is the IDT. If you've done any x86 OS dev, you probably know what this is. In ARM, the CPU will always fault to the IRQ exception handler, and that depends on what exception level you're coming from. From there, in ARM specifically, the OS is responsible for finding the correct handler. So the device that essentially helps the computer keep track of time is the clock device. The clock device is essentially it's literally just a clock on the CPU. It goes off at known intervals. It has a known frequency specifically, and that frequency is typically converted to nanoseconds in software. So with this, because the IRQ goes off at very specific intervals, the OS is pretty easily able to keep track of time, and that helps with scheduling a lot. So finally, what is a context switch? So the context switch is really just a process of switching from an old process to a new process. So a context switch has to accomplish at least the following things. So first, it has to properly pick a new process to run. Properly is a weird word because it really depends on what your scheduler is. So if you have a real-time scheduler, it might be the process that needs to run now. If it's a fair scheduler, there's other heuristics they have to use. It also has to save the old process's general purpose registers, its stack pointer and its program counter. If you do x86, the program counter is the same thing as the instruction pointer. It also has to restore the general purpose registers and stack pointer and program counter of the new process. It also has to switch the page tables and the entire memory state. And finally, it needs to save and restore any model-specific registers or architecture-specific structures. So in x86, an example is FSGS. If you've ever done thread local storage stuff or thread local storage reversing, you should be familiar with FSGS. In ARM, an example is pointer authentication. Pointer authentication is a better mitigation for buffer overflows than stack cookies. So there's two types of context switches. The first type of context switch is a voluntary context switch. A voluntary context switch is when a process explicitly yields control of a CPU to another process. This is typically used when you're blocking. So let's say you're waiting for something to happen, then you essentially just yield control of the CPU to some other process because there's no point in busy looping. The second type is an involuntary context switch. This is when a process is taken off the CPU unwillingly. Involuntary context switches almost exclusively happen when a process exceeds its time slice. So this can be problematic in very specific situations where if you get kicked off the CPU and you're still holding a lock, then you're basically kind of screwed because that would cause a deadlock really easily. That's pretty much only in kernel space though. In user space, mutexes don't fall into that problem. So, but specifically in kernel space, there are ways to disable it, and I'll talk about that at the end. So before we actually talk about the Linux kernel specific stuff, I have to give a little bit brief introduction into the Linux kernel. So if you've taken like MOPS, you should be familiar with what the PCB is, the process control block. In Linux specifically, the process control block is task struct. Task struct is like absolutely fucking massive. I think it's like a page and a half, which is like quite a few thousand bytes. There's a few important members that are used specifically in context switching. There's thread info. Thread info contains a lot of useful information about the current state of the process. And there's one particular element in thread info called the flags that holds a lot of useful information about a process. So it'll contain stuff like if the process needs to be rescheduled, which we'll talk about that, if there's a signal pending, other stuff like that. There's also the struct, which is the memory management struct. That contains all the paging data. So like you have your page global directory thing, and you also have your VMAs and everything else. You also have your thread struct, which is different from thread info. I don't know why they name them so similarly, but you know. So this contains all the Kali saved registers and a lot of the save state of the process when it is switched out. And I'll show that in the code. All right, so now I think I kind of gave most of the context that you need to understand this. Now we get to talk about the code path. Wait, what? Okay. Oh, okay. Yeah. So this is the involuntary context switch. Yeah. So as I talked earlier, an involuntary context switch is when it essentially runs out of its time slice, gets kicked off the CPU. In the Linux kernel specifically, the entry point for the involuntary context switch is the clock interrupt, the clock IRQ, or the ISR. So specifically the code path, this is the code path. This is like the bare bones version. So you start at the clock interrupt, then you go to EL0. Is this clear? Can you guys see this, by the way? Okay. So there's EL0, EL1, IRQ. So that's specifically for ARM. In x86, that would be replaced by the IDT. And then eventually you run a bunch of driver code, and you eventually hit tick periodic. Tick periodic goes into update process times eventually, and it eventually hits a function called scheduler tick. This is where the main work is done. So the first step of scheduler tick is really update run queue clock. Update run queue clock is the code path that allows essentially reads the hardware clock and puts it into software. So this updates a bunch of statistics that are used to make sure that the process is not running for too long. So you hit sched clock CPU, and then you read, so sched clock CPU is the per CPU structure, if you're familiar with that. And then you hit sched clock, and then you do this, you hit this vtable thing right there, the rd read sched clock. So depending on what clock implementation you're using, this is the function that will explicitly read the hardware clock. So in x86, there's some weird APIC stuff, which I'm not really too familiar with. And for ARM, there's a model-specific register. It's like CNVPCT, something like that. So at this point, the runtime statistics are updated. Then with this completed, the scheduler can then run the scheduler, I guess the flavor of scheduler. There's a few flavor of schedulers in the Linux kernel. There's fair and there's real time, sorry. I'm going to be talking about the fair scheduler because the real-time scheduler is extremely complicated. So after it finishes update run queue clock, it goes into the fair scheduler, and that eventually hits entity tick. Entity tick first runs update cur, which updates the runtime statistics in the fair scheduler structures. Then you hit check preempt tick, then resched cur, and then set task need resched. So check preempt tick specifically is essentially the code path that it essentially checks if the process has exceeded its time slice. So if it has, you run resched cur, And resched cur sets a flag called TIF need resched. And that essentially lets the CPU know that in some point in the near future, this process needs to be taken off the CPU. This is kind of useful because we can't do all the work in the IRQ because IRQs need to be fast. So we need to take it off. So we essentially need to set a flag first and defer that work to a little later. Once you have exited from a syscall or an IRQ, or any syscall or IRQ, not necessarily this one, the kernel will always run a thing called exit user mode prepare, which essentially checks if there's any work needs to be done with that thread flag thing. If there is work that needs to be done, like stuff like there's a signal pending or a reschedule is needed, it runs a thing called exit user mode loop, and then that actually does the context switch, which is done by a thing called schedule. So I think I can actually just show you the code, because this is probably not a very good diagram. How much time do I have? I have 20 minutes. Okay. So you can really do, if you do check preempt tick, okay, I'm showing this. This isn't the fair scheduler specifically. So this is the function that specifically makes sure that a process has not exceeded its time slice. So you have this thing called ideal runtime. This is the function that essentially calculates the time slice. This is based on a lot of factors, and the algorithm is actually pretty complicated, so I don't really understand it. But this is the function that gives you your time slice. Then you have delta exec. So delta exec is simply how long the process has been running for. So these two statistics, so this statistic specifically, well, these two statistics rather, were updated at update cur. This function right here, update cur. So this is essentially a up-to-date version of how long the process has been running. So if the process has exceeded its time slice right here, reschedule it. So resched cur, just reschedule it. I'm not sure what this is actually. There's a sysctl called sched min granularity. Not really sure what that means, but I guess if it's less than that, then return. This is actually a particularly interesting one, and this is what enforces fairness, and this is why it's called the fair scheduler. So in the fair scheduler specifically, there's a thing called v runtime. So some exec runtime is the actual number of nanoseconds that it's been running for. V runtime is a weighted nanoseconds. So there's a lot of factors that you can use to essentially increase or decrease the V runtime and how fast it scales. So if you've ever done Linux, you might be familiar with nice values. Nice values are a priority system in the Linux kernel, and that really affects how fast your V runtime goes up. So this pick first entity right here picks the next entity that will be scheduled onto this CPU. So if the difference between the current process's V runtime and the next process's V runtime exceeds the ideal time slice, then you want to reschedule it. So essentially what that means, like in English, is that if the current process has been running for much longer than other processes that need to be rescheduled, then just take it off the CPU. So essentially what this does is essentially enforces the fact that every process should have around the same runtime. And by doing this V runtime system, this V runtime calculation right here, you're able to enforce that. So yeah, this is check preemptive. This is really the work that's kind of interesting. Okay. Okay, so this is the actual process switch. This is what actually switches the process from process A to process B. So at the bottom here, you had schedule. This literally just picks off where this graph ended. So schedule. So schedule hits __ schedule, which is a weird Linux kernel semantic. You might be, if you've done Linux kernel work, you're probably familiar with that type of code style. Then you hit pick next task. So pick next task asks the particular schedule that's being used, give me the next task that should be run on the CPU. And that's really based on what the scheduler wants to return. Then you have an RCU init pointer. This specifically switches this. There's a particular thing on the run queue that initializes that. And then you hit the actual context switch. So there's a literal function called context switch, and that's what actually switches the process state. So the first thing you want to do is switch the page tables. Actually, switch the memory state. So I guess I'll just go over page tables real fast. Page tables are essentially They're essentially the thing that determines the structure of virtual memory. Yeah, if you're familiar with any architecture stuff or familiar with OS dev, you're probably familiar with page tables. But this is essentially what determines what you can access in memory and what you can't, especially as well as the permissions. So this one literally just switches the page tables. So in x86, you might be familiar with CR3. CR3 is the base for the first level of page translation. In ARM, it's TTBR, TTBR0, and TTBR1. And that's switched using CPU do switch MM. Once that's finished, you actually move to the thing that switches the register state. That's called switch 2. So switch 2, there's at the top of, actually, it might just be easier if I just show it instead of just reading off the graph. Yeah, this is the ARM code specifically. So this entire thing right here, these are this is the model specific stuff, the architecture specific stuff. Whereas pointer authentication here, that's for buffer overflow protection. You have stuff like hardware breakpoints. If you're using those, it'll switch those here. Thread local storage as well. It'll switch that here as well. And there's a bunch of other stuff which I'm not completely familiar how that works. And then you do a bunch of other stuff here, a bunch of other architecture specific stuff. And then you do CPU switch 2. This is so CPU switch 2 is a crucial point in the context switch, because after CPU switch 2, specifically when you return from CPU switch 2, you are in a new process. Yeah. So really, you get in CPU switch 2 has 2 arguments. You have the previous task struct and you have the next task struct. The first thing it does, it stores the Kali saved registers into the previous task struct. So that saves the Kali saved registers. The reason you need to save the Kali saved registers and not the caller saved registers is because it is presumed that the function that called CPU switch 2 has already saved those registers. So you really need to save these and restore them after. Then you restore the Kali saved registers for the next process. So this restores its process state. You also have to save the stack pointer and a link register. So the link register, if you've never done ARM, is essentially in x86. Whenever you do a call, like you run the call instruction, you always push the RIP, the next instruction's RIP. ARM has a different way of doing it. They use something called a link register. So instead of pushing it onto the stack, they essentially just move it into a register called the link register. Yeah, so you save the link register, you restore the link register for the new process, and then you return. And that essentially puts you in your new process. And from there, you just return out, and you're essentially in a brand new process. And from here, you've completed your context switch. And the old process has been completely saved, the new process has been restored. Yeah. So as I was talking about earlier, there's one important thing. So involuntary context switches are not necessarily always good. They need to be stopped sometimes, specifically when you're running a critical section. There's 2 ways to stop involuntary context switches. The first way you do it is by disabling IRQs. Disabling IRQs is by far the most effective, but it can be bad because disabling IRQs, because as I discussed back here, the only way to enter this code path, this specific top code path, the yellow code path, is by having the clock interrupt. By disabling IRQs, you just can't have the clock interrupt anymore. So you can't be rescheduled. Yeah. So, but that can also be problematic because you want IRQs and you want to pay attention to devices. So by disabling IRQs, you can just leave a lot of work remaining. Like sometimes you might not get your network packets and other stuff might not happen. The second way is disabling preemption. Disabling preemption also works. Disabling preemption is actually a purely software thing. It's a purely software mechanism. It's actually a preemption count in the Linux kernel. When you disable preemption, IRQs can still happen, but the process is guaranteed not to be switched out. This can still be problematic, especially when you're dealing with if you're using like spin locks that are used in the IRQ handler. Disabling preemption just won't work because yeah, it just won't work because the IRQ will still happen and it'll still trap, and there'll still be a deadlock. So you have to be careful when disabling preemption to make sure that you have to make sure that the lock that you're, I guess, holding when you disable preemption is not being used in any ISR, I guess what I'm trying to say. That's how you stop an involuntary context switch. So what are a voluntary context switch? So voluntary context switches, as I discussed, are where a process defers control of the CPU. In Linux, a voluntary context switch can happen by simply running the schedule function, which is essentially the function that performs the context switch. Voluntary context switches are used to facilitate blocking. So here's the blocking code path. This is how you block in the Linux kernel. So you run this thing called prepare to wait, then you hit schedule, then you check and sometimes and eventually you'll get woken up. Sometimes it might be accidental or spurious, as they say. Then you check the status variable. If the status variable is not satisfied, you just go again. If you do, then you just leave. Yeah. So those are, I guess, all the types of context switches. That's, I guess, the main code path for how it works in the Linux kernel. If you're interested in like more readable diagrams, or just, I have additional notes on my website, on my notes website, notes.minio333.dev. If you're interested in that, and yeah, that's context switches. Yeah, what's up?
So I guess kind of like what was your research process for this? Was just this thing that you like found in the wild? Was this something like
Can't really talk about the research process because it's for my job, but what I can say is that I had to do a project for a client, and eventually I had to realize that using the context switch code path and understanding it was the most effective way to accomplish what the client wanted. So that's how I learned about everything. I essentially had to research everything and understand the code path completely to make sure I didn't break anything when I was doing whatever I needed to do for the client. So that's how I got here. Yeah. And I have been just interested in scheduling for a while now, so it's just been a cool topic. Yeah, what's up? Yeah, because Emmanuel's been yelling at me. I've made like 3 promises to Emmanuel for like 3 different presentations, and I haven't delivered any of them. So I will get onto that. Yeah. Yeah. Okay. Yeah. Any other questions? Okay. Nice.